Lab 3 circuits. So, introduction to this lab. The purpose of this lab was to predict the behavior of circuits containing resistors in series and in parallel. Also to use multimeters to measure the current and potential difference, and then also to observe the behavior of ohmic resistors and capacitors. So this lab demonstrated Ohm's law, which is voltage equals current times resistance. And it also demonstrated Kirchhoff's circuit laws, including the loop rule and node rule. The loop rule is the sum of the potential differences around the loop is equal to 0, and the node rule is the sum of currents flowing into the node is equal to the sum of currents flowing out of the node. So here's a preview of the results. So for the first circuit, which did not have a capacitor, the voltage increased after the 47 ohm resistor and decreased after the 100 ohm resistor, but it stayed the same across the ammeters and wires. And then for the second circuit, which was an RC circuit containing a capacitor, the 10 ohm light bulb had a faster capacitor discharge time but slower charge time, whereas the 20 ohm light bulb had a slower capacitor discharge time but faster charge time. So here are the experiment details. The system was the circuit and the surroundings was everything else. And the initial conditions and assumptions were that the resistance of the ammeter and wires were negligible. So here are all of the measured values for circuit 1, including a diagram of the circuit. As you can see, the initial voltage, total voltage was 3 volts, and it decreased after the first capacitor and increased after the second one. And then for the voltmeter connected across the 100 ohm resistor, it measured 2.5 volts, but when the ammeter was in parallel with the 100 ohm resistor, it was 1.1 volts because the current was split between the resistor and the ammeter. So here are the circuit 1 resistances calculated in the potential graph. The wires and the ammeters had 0 resistance, but the 47 ohm resistor had resistance of 46.667, and the 100 ohm resistor had a resistance of 140 calculated. And then here you can see the potential graph as well throughout the circuit. So for circuit 2, which is an RC circuit, the conditions were 2 1.5 volt batteries, one 1F capacitor, and then 2 light bulbs, one 10 ohm and one 20 ohm, which we tested separately, and then the ammeter was 15 milliamps. So we found that the 10 ohm light bulb, the capacitor had a faster discharge time and slower charge time, whereas with the 20 ohm light bulb, the capacitor had a slower discharge time but faster charge time. And basically what happened was, as the capacitor charges, the brightness of the bulb decreases until the current is decreased down to 0, and the same thing when you remove the battery to discharge the capacitor, the brightness of the light bulb decreases over time. So for the what if you charged a capacitor with no resistor in the circuit? So the capacitor would charge instantly according to an ideal model in which there's no resistance in the circuit, because there would be nothing to resist the current flowing. But in actuality, even if there isn't a resistor in the circuit, components of the circuit will have some resistance, like the wires, for example. However, in this lab, we assumed the wires to be negligible. So the capacitor would not be charged instantly due to being slowed down by even just like minor resistance within the circuit. Some potential sources of error could be the equipment used in lab could potentially cause problems if it was like defective, or the batteries were old and the charges weren't accurate, things like that. And yeah, like continuing on, damage, wear, tear to the equipment. And then also human error in building the circuits and recording the time could be a potential error, or just error in like measuring the voltages and stuff. That's all. Thank you.